Okay, I guess we can start. Um, so, welcome everyone. I'm Atan. Um, I'm a mathematician that transitioned to cryptography a few years ago. Before that, I was many years in academia. Um, this course is a second version. There was a course that started in August last year, and is now pretty advanced. Let's say in a month and a half, I expect that we start proving the properties of the whale pairing. So all in all, it would be like a year and 3 months to cover the material, and that's roughly the estimate for this course as well. What happened with this course is that we started a hybrid version in which we meet in the Ethereum Berlin office, and there are like participants from the office, but also online people. And we realized that we don't have a lot of people participating. Keeping in mind also that people tend to drop out at some point. And that's why we advertised it again. And it's good to see you guys. I hope many of you will stay. And so what is generally planned is there are YouTube videos of I think 6 sessions that we did. Each of them is about 2 hours video. And I have to go to a conference next week for about 3 weeks. So we rejoin, or we start again in about a month from now. I think it's like August 9, August 8. And what I want to ask you is to watch the videos, make some questions if you like. We have a Discord channel, so I will still be available to answer questions on Discord. Then when I'm back, I think we can do maybe another recap session, or even 2. And we start from where the videos stopped, which is more or less quotient groups. Now, in the first video in YouTube, I say what this course is about, but let me repeat. There is somewhat of a gap in the literature concerning pairing-based cryptography mathematics. The reason is that elliptic curves are usually taught at a master level in pure math. And if you try to read the mathematical literature, it's not elementary. It assumes you have an undergraduate degree in math, which is quite a lot. And on the other hand, the cryptography literature is elementary, but it doesn't give you the proofs. So this course is designed to fill in this gap, which means we do almost all the proofs. It really means that you get, at the end of the course, you get, let's say, up to an early research level in pairing-based cryptography. Now, you can ask, why do you need it? And it's a valid question. I mean, the weak reason, you could say, is that if you really want to know that something is true, you want to know the proofs. But it's kind of a weak reason, because you can believe many decades of mathematical community deliberation, and you know, it's pretty solid as it is now. But I think that the stronger reason for making the effort in learning the proofs is that that's really the way to learn how to reason about these mathematical objects. And eventually, once you work with pairing-based cryptography protocols, you might need to tweak something. You might need to look at something else that is not in the protocol, and for that you really need to reason about these notions. Now, the course is designed for people with only high school background, but it takes a significant mental effort if you don't have the background, which means you need to, I mean, apart from the 2 hours weekly session, to go over the session, let's say 1 or 2 hours in addition. There are no certificates, no exams, so it's all about you and what you want to learn. But keep in mind that it's not so good to miss sessions if you don't have a lot of background, because things really closely rely on each other, and you lose the rope very quickly if you let's say don't come to the session and then also don't watch it on YouTube. The basic template of almost every mathematical text is definitions or constructions, examples for these new notions that the definitions talk about, and propositions and theorems. Definitions you need to remember, because whatever we talk about would rely on a certain definition. I can remind you, and I will do it often, but eventually you need to remember the definition. Of course, over time, if you follow the string of the story, it's, I mean, you kind of you tend to remember the definition because it's being used a lot. The proofs, you need to be able to follow every step of the proof. So it's a bit like I mean the ideal situation is when it's airtight, you understand every step of the proof and the conclusion. If a little bit of air goes away, it's okay. But if too much, you can't fly. Now, apart from this, because eventually we will get into a somewhat advanced material in math, it requires maturity. Maturity is kind of understanding why certain definitions are made. I mean, usually definitions are in close tie with propositions and theorems. I mean, you want to define something that will be eventually well behaved. And maturity is a matter of experience. So, of course, if you don't have background, it will take you time. But I think that a way to accelerate the maturity is to have some kind of good philosophy about what is going on. So I will often offer my take of a little bit of philosophy. You can have yours and so on, but I think it's worth to make some room for it. Now, the best way to learn is to ask questions. And you could say there are strict kind of questions, which mean whether something is well defined, or why a certain step in a proof is true. And there are soft kinds of questions, which are what motivates the discussion, the definition, the theorem, how to get a more conceptualized understanding. And of course, the more questions you ask, the better you learn. And most importantly, you should put your ego aside and not be ashamed to ask silly questions. It's the best way, the quickest way to learn. People among you that don't have background may have just questions about notation, about terminology, and so on. All of that is welcome. I just ask that we do, you raise a hand when you want to ask something, and I can hear it, and I'll be happy to have many questions. I think that's about it from my side on the course. Do you have any questions? Okay, so one thing I forgot to mention, but it's written in the announcement and so on. There are notes for this course. It's pretty much in a form of a book. I typically follow closely the notes, and you can always find an updated version on my website, and I strongly recommend that you take a look at the notes. You could even do it while the session is going. There is, I mean, one disadvantage of what I have in the notes is that there are not many exercises. One reason is that, especially in the advanced part, because we follow a non-conventional path, it's not so easy to find exercises. I mean, the ones in typical math textbooks might be out of reach for you because we didn't follow the path that the other book follows. But also, I think over time, I will add some exercises. It's good to do the exercises, and I will sometimes mention exercises as part of the lecture. But because of time limitation and so on, I cannot give you much of a feedback on exercises. So that's one of the disadvantage of this course. Nevertheless, in my experience, it should be possible, although challenging, it should be possible for average person that has a high school background to follow the course entirely. Yeah, so that's about the generalities of the course. Can we do a quick vote of who actually watched some of the videos? Let's say maybe you can write something in the chat. Okay, and do you think you can? I mean, in the coming month, you can watch these 6 videos. Yeah, we can do one. I mean, we can postpone a little bit the next session if you want, or we can do. I think what we can do is on August 8th, I do a recap or Q&A and recap. And then you have another week to watch the, I don't know, the remaining videos you didn't watch. And so it's almost one video per week, and then we can start again. Okay. Now, as for the material, is all it should be all linked in the Twitter post that we had a while ago. I will. There's also a Discord channel. I don't have the links with me at the moment, but if you are registered, then we have your emails, and you will get it from there. Or maybe someone here in this call have the links, and we and can send it in the chat. Maybe. Hang on. Okay, I think I found the link to the YouTube videos. This is basically the Ethereum Foundation channel on YouTube. And this is the link to my website. Okay, so what is an elliptic curve? You know that I assume that most of you have seen it before, that if I take a prime number p, and I take all the numbers up to p minus 1, I will call this thing fp, and on fp we have two binary operations that are addition modulo p and multiplication modulo p. Modulo p here means that I do, I mean, modulus is like clock arithmetic. So you know that if you have time 11 plus 2, then it's 1. It's because we do, I mean, so clock arithmetic is modulus 12. I do addition or multiplication of the clock hours, and I reduce, I mean, I remove all the maximum amount of multiple of 12 from the result, and I remain with some number between 1 and 12, and 12 is, let's say, not included. But you can do this for any positive integer. I mean, I can do some modulo 2 would be I take the number 0, 1, and I can do addition and multiplication. Modulo 2, I get the usual binary representation. But if I do it for a prime number, then These addition and multiplication, they make FP, this is called a field. The main property that a field has, and if P is not prime, we will not get it, is that mainly for any non-zero element in FP, there exists some element which I denote as A minus 1, such that A times A minus 1 is equal to 1 modulo P. Now, an elliptic curve is an equation of the form y square equals x cubed plus ax plus b. And there is a question of where the constants a and b come from. So if a and b are real numbers, then I can look at the solution set of this equation. The solution set is a collection of pairs x comma y that satisfy this equation. So let's say the solution set of E is the set of all pairs x comma y in the two-dimensional plane R2, such that y squared equals x cubed plus ax plus b. If you want, maybe a more elementary example, I can take, let's call it P. P is the equation y equals x squared. And I can take the solution set of P over the real numbers. This is the set of all pairs x comma y, such that y is equal to x squared. And if you draw P on the xy plane, then you get a parabola. So this is typical in a field called algebraic geometry, that we look at solution set of polynomials, but polynomials not necessarily in one variable, usually in two or more variables. And the solution set of such a polynomial, it has a geometry usually. So elliptic curve is another polynomial in two variables. And if you look at the solution set over the real numbers, you get a picture like this. And this kind of object is special in the sense that it has a binary operation on the points of the curve. The binary operation is quite simple. I mean, let's say you take 2 points, Q, or let's say P and Q. You draw the line between P and Q. This line has to intersect the curve in a third point, which I would call P star Q. The reason it has to intersect the curve in another point is because of this these three here. I mean, what we have is a degree 3 polynomial, and degree 3 polynomial typically it intersects a line in 3 points. Just like here, a degree 2 polynomial would typically intersect a line in 2 points. So in the elliptic curve, I take these 2 points, P and Q, and I draw the line. I know that it intersects the curve in another point. And since the curve is symmetric along the x-axis, I can reflect my result, and this is called P plus Q. And it's maybe a surprising fact, and it's pretty non-trivial to prove that what you get here is an abelian group. Which is a notion we didn't discuss yet, but a abelian group is simply a set together with a binary operation that satisfy natural axioms. So the typical abelian group that you know is the integers. The integers. Z is an abelian group. And so what we get is it's an interesting object because on the one hand it has a geometry, and on the other hand it has an algebraic structure, this abelian group. So this is algebra geometric object. And it turns out that not only that it has this abelian group structure, but that the abelian group resulting from an elliptic curve has additional properties that most abelian groups do not have. And that is this bilinear pairing. And so the reason people are interested in elliptic curves in cryptography is, well, first, because this is one example of a group, and groups are used widely in cryptography. But second, the pairing that the group of an elliptic curve admits is give you possibilities to design cryptographic protocols that you could not do with just a regular abelian group. And so it became actually, even in ordinary cryptographic protocols that only involve groups, people tend to use elliptic curves quite a lot, or at least that's what I hear from Dan Bonnet. And then in many parts of cryptography that use pairings, I mean, elliptic curves are essential. I mean, there is no other way. There is no known other way to use pairings without elliptic curves. So, okay, so this is, I mean, this is where we're going. I mean, we will try to understand these objects and eventually define the pairings. But in order to do this, we need quite some background. Of course, it is, I mean, it is designed, I mean, I designed the lectures on this part so that only the necessary background, almost only the necessary background would be presented, and of course you can read about it in the literature if you want. But what we need is first, we need to learn about the basic syntax of mathematics. The basic syntax in modern mathematics is a set theory. So in set theory, you have sets. A set is a collection of objects. Let's say a set S is a collection of objects such that for any object X in universe, we can say whether X is an object of A, sorry, of S, or, well, and this is denoted X belongs to S, or X is not an object, not, I guess, element here is a better term. Is not an element of S, And this is denoted as X does not belong to S. And then set theory has a certain syntax that you need to be familiar with. Set theory has generally two versions. I mean, you have axiomatic set theory. This is logic, and this is something we will skip. And you have naive set theory, which is essentially the syntax of set theory explained to use it on a regular math discussion. The second component that we need, so the videos talk about set theory a little bit. Then the important part in set theory that I would recommend you to pay special attention is this equivalence relations. Equivalence relations is a procedure that allows you to kind of glue certain elements in a set and get a modified a quotient set with respect to certain relation. So I will not give the definition here, but maybe intuitively you can understand it by an example. And the example is you take S to be the integers, and you can declare A and B in S to be equivalent if, or if and only if, this is, by the way, usually abbreviated as IFF, and I declare A and B to be equivalent if A is equal to B modulo N. That is, if after I do long division of A by N and of B by N, I get the same remainder, right? I can always write A is some kind of QA times N plus some remainder, let's say remainder of A, and B is some QB times N plus some remainder. And A is equal to B modulo N, by definition, if RA is equal to RB as integers. And then you can say, okay, so after I have this equivalence relation, or after I declare two elements to be equivalent, two integers to be equivalent, if and only if they are equal modulo N, what do I get when I quotient out, when I mod out this equivalence relation? I mean, I want to look at the integers from the the point of view of this relation. So I don't care if n is equal to, or let's say, yeah, if n is equal to, I don't care if you talk to me about 2 or about 4 or about 6. They're all equivalent modulo 2. So when I contract this equivalence, what I get, integers contracted by this modulo n relation, is what is usually denoted as Zn. And here it's one way to represent it is to look at the numbers 0 up to n minus 1. And this is an exhaustive list of representatives for integers modulo n. Because every other integer would be equivalent to one of these elements in this list modulo n. So you see, equivalence relations allow you to make an important construction that we will care about, and this is one example, but there are many more examples of equivalence relations. So I suggest that you pay special attention to this topic. Any questions so far? Before I get to the second component of. Okay, so the second ingredient that we have in also in the YouTube videos, we start to talk about groups. And I think many of you saw things about groups before. It's very typical for people who do cryptography, but nevertheless, it's good to do a review of what we talk about when we talk about groups. That is one thing to notice, is that not every group is a billion. So a group is a billion if the binary operation, let me take a step back. So a group is a set G with a binary operation typically denoted as a dot. So dot, I did not define it, but when I say binary operation, this means that I take two elements in the set G. So the collection of all pairs of elements of G is denoted as G times G. This is another thing that comes up in the Parton set theory. This is what is called the Cartesian product. And a binary operation is simply a function from the Cartesian product of G with itself into G. And a group is a set with a binary operation and a specified element which I denote as 1, such that you have 3 natural axioms. One is that for any A, B, and C in G, if you do multiplication in this way, it's the same as doing multiplication in the other way. This is called associativity. And if you think about it, associativity is something that we almost always want when we have a binary operation, because once we start to get equations or expressions of complicated things that we did with the binary operation, we want to know that it doesn't matter where we put the brackets. I mean, if we know that this axiom of associativity holds, then we can write A times B times C, and this is unambiguous. I mean, whatever place you put the brackets, you get the same thing. So this associativity is a crucial axiom for pretty much any binary operation that we have. And that, as a funny thing, I mean, if you look at the homomorphic encryption schemes, they were unable to make ciphertext multiplication associative. So this is one of the biggest drawbacks in current schemes, is that you don't have associativity of multiplication of ciphertext. The second axiom of a group is I guess you can call it unitarity. So let's say the operation is unitary if for any A in G, A times 1 is equal to 1 times A and is equal to A. And the third axiom is that for any A in G, there exists some element which we call A minus 1, such that A times A minus 1 is equal to 1. So this is usually called a multiplicative inverse. What I want you to note is that we do not assume that the group is a billion. That is a group is a billion if for any A and B in G, A times B is equal to B times A. And part of the development of groups that I do in the YouTube videos do not assume that the group is a billion. Now, in cryptography, and especially in pairing-based cryptography, we use almost only abelian groups. But nevertheless, we sometimes use non-abelian groups, and it's important to understand a little bit of a more general version that is a group that is not necessarily abelian. And after a short while, I just talk only about abelian groups. So pay attention to this distinction. Yeah, I guess usually what we do is I take a 10 minutes break after an hour, and then we continue. But maybe now is a good time for questions if you have. Eniko, what do you think?
Hey, yeah, I have a lot of catch up to do, but some of it makes sense. Yeah.
Can you say again? I couldn't hear you well. Okay, so all right. Let's take a break, and we meet again in 10. Okay, so maybe before I start again, do you have any questions on what we what I said earlier? Yeah, but speak up, Emmanuel. Emmanuel, can you? Okay. Yes. Um, we will, of course. So, one thing that we still didn't cover, I mean, it's not covered in the YouTube videos, but it will certainly be covered, is this notion of homomorphism of groups. And this is like a repeating theme in what we will do. I mean, once we have a notion, in this case, a group, we want to be able to move between two instances of this notion. So let's say if G and H are groups, let's say G is given by, I have multiplication in G, but I have also one in H, so I disambiguate it by this notation. And I have a unit element in G, but I also have one in H, so I call this one sub G. Yes. Typically, people write it as a tuple like this. And H is the same. I have the set, the binary operation, and the unit element. Homomorphism from F to G, sorry, from G to H, is a function F from G to H, such that for any A and B in G, F of A times B is F of A, but here the multiplication is in G. This is F of A multiplied in H by F of B. And let's say F of the unit element in G is the unit element in H, and F of an inverse of an element, a multiplicative inverse of an element in G, is equal to F of this element, and then applying multiplicative inverse in H. So a homomorphism is the natural notion that we want if we want to a function between these two groups, two instances of this notion of a group that preserves the structure or is compatible with the structure. So compatible with the structure is expressed by these three conditions. And what will happen with almost every notion that we get our hands on, we will want to have a notion of like a morphism between two instances of this notion. And this will be true for, of course, for groups. It's also true for sets. Sets, they have no additional structure, so a morphism between set is just a function. But we will talk about fields. Fields are, it's like a group. It's a set with binary operation, but it has two binary operations. When we typically call them multiplication and addition. And these operations need to satisfy some axioms. And after we define the notion of a field, we will have a notion of a morphism between fields that is a function between the underlying sets of the fields that preserve the structure. And later on, we will talk about elliptic curves. But again, if we have two instances of, we have two elliptic curves, we want to know what is the correct notion of a morphism between elliptic curves. So this is a repeating theme in all this course, is that we want to not only have not only study a particular instance of a notion, but rather the interaction between various instances. And for that, we need a notion of morphisms. Is this answering your question, Emmanuel? Well, I'm trying to understand what you're after, but I don't quite get it. I mean, obviously, understanding homomorphisms is important in ZK. When you say to go from the structure of vector spaces to polynomials, it's not quite clear what you mean. I mean, vector space is one kind of notion that actually we will mostly avoid. And a polynomial is on a different level of resolution. I mean, okay. I think I understand what is the gap here. But this, I should say, I mean, this course will not review specific protocols of ZK or otherwise. We do the math. It is mostly pure math. We will do a little bit of algorithms, but for sure we will not cover specific protocols. I mean, the familiar ones, snarks and starks. You will be able at the end of the course, you will be able to read these protocols yourself and understand all the mathematics. But of course, the mathematics is not the only thing, and there are many questions on implementations and so on. So that's kind of the limitations of what this course offers. But I can assure you, Emmanuel, that you will understand polynomials and pairings and so on if you follow. Yeah, go ahead. Okay. Yeah, homomorphism is important to any, almost anything you want to say about either groups or fields or elliptic curves. You need homomorphisms. It's not a big deal. I mean, the definition of a homomorphism I just gave here. It's very easy to, or rather easy to understand, but you want to get familiar with or comfortable with the notion so that you can use it in various situations. And we will have many examples of homomorphisms. And so, yeah, so this is coming up. Other questions? Okay, so this is groups. Another thing we will talk about is fields. This is not this is not something that is part of the YouTube videos at the moment. So you really don't need to understand it well, but just to tell you where this is going. I mean, a field is a set F together with two binary operations. Let's say plus F and multiplication F. And specified elements zero sub F, one sub F, with axioms that you would expect generally for multiplication and addition, and a 0 and 1, satisfying some axioms. For example, you want it for any A, B, and C in F. If I do A times B plus C, then it's the same as doing A times B plus A times C. And you would want that 1 times A is A, and that 0 times A is 0. Okay, so this is like an abstraction of what you know about uh, what we have with ordinary numbers, either integers or real numbers. And once I have two binary operations, I can talk about polynomials. So a polynomial over a field F is a formal expression let's say f of x is equal to a0, this is the free coefficient, plus a1x plus a2x squared up to an x to the n, where n is some natural number arbitrary. And we denote n is called the degree of the polynomial. And you see what I did here, I mean, if let's say x0 is an element in F, we can substitute F, or evaluate the polynomial at x0, and what we get is a0 plus a1 x0 plus an x0 to the n. And you see what I do here, I mean, in every such expression, I do multiplication. And between two such expressions, I do addition. So I need some kind of object that has both addition and multiplication in order to talk about polynomials. And so a field is a natural choice. It's not the only choice. You can talk about rings. These are slightly weaker objects that slightly weaker notion than that of a field, in which you can still talk about polynomials. And as a side remark, in a lot of the mathematical literature around elliptic curves, there is a lot of discussion about rings. And we will, one of the simplifications that we will do is that we will mostly avoid a discussion about rings, because it's easier to talk about fields, and most of the stuff can be circumvented from ring theory. So you see, once we have a field, we can talk about polynomials. And once we can talk about polynomials, we can talk about a solution set of a given polynomial. So, of course, this is polynomial in one variable. one variable that is x. But we can do the same trick with two variables, let's say x and y. So a polynomial in two variables over f is a formal expression let's say f x y is equal to a0, or maybe we can do a00 plus a01 I guess a10 is better. 10 x plus a01 y plus a11 x y plus a20, this is times x squared y to the 0, and so on, right? Up to some level, we have some a and k, x to the n, y to the k. Where, of course, this I didn't say earlier, but I hope maybe you caught it. I mean, here in a polynomial, the coefficients need to be elements in the field. So for any I, AI is an element in the field, and the same here for any I and for any j. So let's say for any I between 0 and n, and for any j between 0 and k, aij is an element in the field. And now if you give me a pair of elements in the field, if x0, y0 are two elements in the field, then I can substitute x0 and y0 into f, and I get some element in the field. So now I can talk about the solution set of a polynomial, in this case in two variables. The solution set of f is the set of all pairs x, y, such that f of xy is going to be equal to 0. 0, and here 0 means the 0 element in the field. So you see, the discussion about fields and about polynomials is meant to give us at least a syntax to talk about solution sets that will eventually bring us to elliptic curves. So we will discuss a lot about fields, a lot about polynomials over fields. One thing that so this is the all the prerequisites for elliptic curves, and what we want, I mean, everything in cryptography is typically finite. This is general a general truth about computer science mathematics, that it tends to have a lot of emphasis about finite mathematical objects. So when it comes to our interest, um, the main goal in the preliminaries let's say main goals. So one is we want to classify finite abelian groups. And two, we want to classify finite fields. Now, what does it mean to classify? This is a kind of a soft mathematical statement. To classify a collection of objects usually means to give a short and convenient description of these objects. I mean, you can say, okay, so we gave a definition for an abelian group, right? This is like a definition of a group with an additional axiom that the multiplication is commutative. Finite abelian group simply means it's an abelian group that has finitely many elements. Same for field. And so, okay, so we have a definition. We know, in theory, we know what are what is a finite abelian group. But it's a very abstract definition. And it turns out, for example, in the first classification issue, we will be able to express every finite abelian group as a combination, let's say a product of integers modulo n for various n. So this is a very convenient. It's a very convenient tool. I mean, because integers modulo n we understand very well. It's clock arithmetic and so on. Product of integers modulo n, okay, it could be a bit more complicated, but is still manageable. And it turns out that every finite abelian group is a product of these integers modulo n up to isomorphism. Isomorphism is well, another notion that we will discuss that tells you when two groups are essentially the same. They are not the same on the nose, but they are, let's say, from the point of view of a computer, they will be the same. And in two, to classify finite fields, it turns out that for any p, and any positive integer there is an essentially unique field um, this is denoted as fp to the n, or also gf n um, of p to the n elements. And that's it. I mean, every other finite field has to be isomorphic to one of these fields. And so, to sum up, the first part of the course will focus on these, I mean, these two classification statements. Once we have it, we are ready to move to elliptic curves and continue the development of these latter objects. Maybe it's a good time to pause for more questions, if you have any. Okay, so I I don't want to go too far. I mean, I think this is a good description of the near future, and the rest you can, of course, read in the notes and so on. And what I ask again is that you watch the videos. You have a link to the Discord channel, and you can ask questions about the existing material on the Discord. I will be available there. And we meet again on the 9th of August to do another recap and Q&A. And after that, I guess it would be, sorry, it's the 8th of August. And then on the 15th, we just start from where the videos stopped. Any famous last words? Yes. So, Ali, you have this a link in the chat here that I sent. You see it? It's the only YouTube link, I think. So it's all the videos there. I think it's 6. Yeah, probably I will. We will upload this session as well, but I need to make sure with some people before we do it. All right, then have a good time.